Okay, so we're gonna continue our discussion on chapter 6. And we're gonna move on now to the topic of calorimetry, which is basically dealing with how do we measure heat flow. So we're gonna look at how do we in practice determine the amount of heat that is either produced or absorbed in a chemical reaction. And the device that we use to do this is called the calorimeter, all right? Now, there are different levels of sophistication in terms of this particular type of device. The one that you see here is basically the ultimate in low tech, because basically what is used in this version of the calorimeter is 2 styrofoam cups, which has a cover here, kind of stopper with 2 holes in it, one of which you're going to push through a thermometer, and the other one you're going to push through a stirrer, all right? So the thermometer, of course, the function of the thermometer is to measure the temperature increase, and the function of the stirrer is to make sure that the contents inside the styrofoam cup is thoroughly mixed, all right? And basically, just to give you a brief overview of how this works, let's say you're doing a reaction between 2 substances that are exothermic. So basically, you have to make sure you have the right molarity, you measure the correct volume and all that stuff, you mix them together. Well, firstly, when you mix them together, record the initial temperature, and then you wait until the temperature rises to the maximum value, and you record that temperature. And the difference between the 2 temperatures, of course, is what you're going to use to determine the amount of heat that is produced in the reaction. And then based on those numbers, you can basically determine the heat of the reaction, all right? Now, the picture that you see down here to the bottom left of the screen is a more sophisticated type of calorimeter, which is used specifically to measure the heat change in a combustion reaction, right? And this is in particular used for organic compounds. So you burn the organic compound, typically heat will be released, and basically this is designed in order for you to measure the amount of heat that is produced, and therefore you can, based on the data collected, determine the heat of the reaction. So let me just briefly describe what's happening here. Encased in this steel bomb, which is basically a kind of compartment, you're going to have your organic compounds here. You have 2 lead wires leading into the compound here, which is placed on this dish. And basically what you're going to do is ignite the compound here. Of course, you know that for organic compounds, when they're burnt, they produce, among other things, depending on the compound, carbon dioxide and water and heat, right? So you're going to end up with carbon dioxide and water inside here. You're also going to have heat generated, which will be transmitted to the water outside. So the heat will pass through the walls of the bomb and get into the water out here. Of course, the amount of water that you have started off with, you'd have to measure that and record that value as well. And then based on the temperature increase registered by the thermometer here, then you can, again, just like we described here, determine the amount of heat that is produced in the reaction. And of course, there's a little spinning thing right here, which is used to make sure that the heat is basically spread uniformly throughout the water, all right? So this is more complex in terms of design, and that's because this is specifically for determining the heat of combustion of an organic compound. Okay, so with that said, let's come to some definitions, some of which you should have met before in your introductory or high school chemistry. Now, when it comes to calorimetry, basically, as I said before, it is used to measure the amount of heat that is either evolved from the reaction or absorbed from the reaction. Now, if we assume that the reaction is exothermic, if heat is produced as a result of the reaction taking place in the calorimeter, that means that the heat will be absorbed by the calorimeter, right? So basically, we can write down a relationship between the heat that is generated by the reaction and the heat that is absorbed, and that would be simply Q reaction is equal to minus Q of the calorimeter, all right? Q reaction is equal to minus Q of the calorimeter. And the minus sign is very important. It indicates that basically whatever the amount of heat that is produced by the reaction, the amount of heat that is absorbed by the calorimeter will be the same. So therefore, Q reaction would be negative if the reaction is exothermic, and Q calorie would be positive as a result. All right. Now, one important aspect of the measurement of the heat flow is to record the temperature change, right? So basically, we have to make sure that we record the initial temperature upon mixing of the different substances and the temperature at the end of the reaction, right? So that's very important, all right? And the temperature change, of course, will be the final temperature minus the initial temperature. So delta T, change in temperature, would be the final temperature minus the initial temperature, all right? If you recall, I think I said this the last time, especially when it comes to this particular chapter, whenever you hear change of any value, it's always the final minus the initial, all right? Now, here's a term that I need to introduce to you. It's called the heat capacity, right? It is the amount of heat required to change the temperature of the system by 1 degree Celsius or 1 Kelvin. And let me just say that it doesn't matter if the change is expressed in degrees Celsius or Kelvin, the result will still be the same, all right? So that's the definition of the heat capacity. And therefore we can represent the relationship, excuse me, we can represent the relationship between the heat capacity and the change in temperature according to this equation I'm about to show you. Okay, so this is the equation right here. So uppercase C is the heat capacity, right? Q is the heat change, and delta T is the change in temperature, all right? And therefore the units of heat capacity would be joules per degree Celsius, or right here, or joules per Kelvin, right? Again, it doesn't matter if the units are expressed in this or this combination, the results, the calculations will still be the same, all right? So that's the heat capacity of a system. Then there's another definition I need to give you, and that is the molar heat capacity. Now this one, I'll be honest with you, I don't anticipate you guys using this in this particular chapter, but I'm just going to give you anyway. The molar heat capacity is the heat capacity of 1 mole of a substance, right? So basically, to get the molar heat capacity, whatever the heat capacity that you get here, you divide by the moles of the substance involved in the reaction. Another definition, which you will definitely be using in this particular chapter, is what is called the specific heat. In some textbooks, they call it the specific heat capacity. So let me just add that. I can get this pen working. Okay, so in some textbooks, they call it the specific heat capacity. All right, or simply called specific heat. Same thing, right? And the definition is it is the heat capacity of 1 gram of a pure substance, right? So basically, the relationship between specific heat and the heat capacity is given by this expression right here. Yeah, so lowercase c is the specific heat, uppercase C is the heat capacity. So this is the relationship here. C, lowercase c is equal to uppercase C divided by M. Now we already know that uppercase C is equal to Q divided by delta T. So if you plug this where C is, you're going to end up with this equation right here. And we can rearrange it to get it to be equal to that, which is the more familiar way of expressing the relationship between Q, C, M, and delta T. So Q is the heat change, C is the specific heat, M is the mass of the substance, and delta T will be the temperature change, which is the final temperature minus the initial temperature, all right? So that's the relationship that you're going to be using. In fact, we're going to use this equation in some examples shortly, all right? Okay, so that's it. In fact, we're going to use it right here in this example. Let me clear this here. So this question says, Hold on. Oh, I thought, hold on. Oh, okay, here's the question. So this question says, calculate the heat capacity of an aluminum block that must absorb 629 joules of heat from its surroundings in order for its temperature to rise from 22 degrees Celsius to 145 degrees Celsius. Now, this one is asking for the heat capacity, not the specific heat. I misspoke earlier, all right? So basically, this is the equation you're going to use. I'm going to do it over here, up top. Uppercase C is equal to Q divided by delta T, right? Now, you have to be careful about the signs as well. If you remember, I said that, when you're doing these questions, you have to make sure that you interpret the questions so that you know what signs to use in regards to different values that are given. Because the question says that the aluminum block absorbs 629 joules of heat. So what does that say about the sign of Q? If the substance is absorbing heat, then the sign is what?
Negative?
Nope, it's absorbing.
Oh, taking in.
It's positive, right? So therefore, this will be plus 629 joules, right? And then now, for delta T, that's a change in temperature. Remember, the change in temperature is always final minus initial, right? So the final temperature is 145, that's T2. The initial temperature is T1. So we're going to put that down here. So that would be 145 degrees Celsius minus 22 degrees Celsius. And that's it. So if we work on the bottom part first, that's 145 minus 22. So that gives 123. So that plus 629 joules over 123 degrees Celsius. And then we do the number crunching, 629 divided by 123. And according to my calculations, I got 5.11 joules per degrees Celsius. And that would be the answer. All right, that would be the specific heat. Not the specific heat, the heat capacity. Okay, any questions about this? Any questions about this example? Any questions? Okay, so clear this. Let's go down to the next slide. So let's talk about in more detail this whole concept of specific heat, right? So basically, that's the equation that I introduced to you earlier, which relates the heat change to the mass of the substance, the specific heat of the substance, and the change in temperature, right? Couple of things I want to mention here. If the change in temperature is positive, right? So in other words, if the final temperature is greater than the initial temperature, then that means that heat is gained by the system, which means that Q must be positive, right? So applying that to this equation, if delta T is positive, right, the specific heat is always positive and the mass is always positive. So that means that if delta T is positive, that means that Q is positive, right? On the other hand, if delta T is negative, right, even though these two are still positive, that means that Q would be negative, which means that the substance is losing heat, all right? A bit of information here concerning the units. The unit of Q, the SI unit of Q, the heat change, is in joules. But there's another unit, which is not an SI unit, which is called the calorie unit, which is still used in chemistry and other sciences, right? So even though it's not a metric unit, we still use it. So the definition of the calorie unit is basically based on the properties of water, right? And basically, as a result of that definition, water has a specific heat of 1 calorie per gram degree Celsius, right? And there's a relationship between the calorie unit and the joule unit, which is given right here. And this is also available in the packet that is posted in Canvas, which you'll have access to during your future test, all right? So this is basically the relationship between the calorie unit and the joule unit, all right? And there's another unit of energy which is used specifically by nutritionists. It's called the food calorie, right? And the unit of that is slightly different compared to the unit of the calorie that we're accustomed to. The food calorie is uppercase CAL, that's the unit, or it's the same thing as kilocalorie, right? And that is equal to 1,000 calories that we're accustomed to, right? So that particular unit is used to express the energy content of food and so on in the area of nutrition. We don't really use it that much in, chemistry, for example, all right? Okay, and here we have a list of different substances and their specific heat. You need to recognize that a specific heat for a substance is a physical property, right? Like density and so on, right? So different substances will have different values for specific heat, right? And what you notice is that metals typically have low values, relatively speaking. So if you look at this short table here, iron has a value of 0.449 joules per gram degree Celsius, lead is 0.128, mercury is 0.139, and so on. So metals, they tend to have relatively low specific heat. Liquids tend to be a bit higher, and when it comes to water, as far as I know, water has the highest value for its specific heat, which is 4.180 joules per gram degree Celsius. And the main reason for that has to do with a phenomenon known as hydrogen bonding, all right? And later on in chapter, much later on in this course, we're going to learn about hydrogen bonding and how it affects specific heat value. Okay, so that's basically it as far as specific heats values at 25 degrees Celsius. So let's look at some examples, right? So I'm going to need some space again for this one. So let me copy and paste this onto Word. Let me go here. What's going on here? Okay. Just wondering. And let me this. Okay, so this is the question right here. It's asking how much heat in joules and in kilojoules does it take to raise the temperature of 225 degrees grams of water from 25.0 degrees to 100 degrees Celsius, all right? So the equation that you're going to use, of course, is the one I just showed you, which is Q is equal to M times C times delta T, right? So M is equal to 225 grams. The initial temperature T1 is 25 degrees Celsius, and the final temperature T2 is 100 degrees Celsius. So all we have to do is plug the numbers in. So 225 grams. Now C would have to be given, which I showed you in the previous slide. That would be equal to 4.184 joules per gram degrees Celsius. And then as far as the change in temperature is concerned, that will be T2 minus T1, which would be 100.0 degrees Celsius minus 25.0 degrees Celsius. And that's basically the setup. Of course, this part here will work out first. That will be equal to 75 degrees Celsius. In fact, 75.0 degrees Celsius. And then we do the rest of the calculations. So that will be 225 times 4.184 times 75. And then according to my calculation, that works out to be equal to 7.06 times 10 to the minus 4. And the units here would be joules, because the grams will cancel out here and here. Degrees Celsius will cancel out here and here. So the only unit remaining would be joules. And that would be the answer. All right. Any questions about this one? Any questions? Okay. let me go back to the PowerPoint and let's look at this example. Again, I'm going to copy and paste this. Go Control C. Let me get rid of all this here. Okay, so this question is asking, what will be the final temperature if a 5.00 gram silver ring at 37 degrees Celsius gives off, and that's very important, again, pay attention to these terms, gives off 25.0 joules of heat to its surrounding. And it says, use the specific heat of silver listed in table 6.1. So the table I just showed you, I need to go back to it to get that value. You go back up here. Okay, for silver, it's 0.235, all right? So, so the value here for the specific heat is 0.235 joules per gram degrees Celsius, all right? Okay, so the question is asking for the final temperature, right? So the equation, remember, is Q is equal to M times C times delta T. Now, what I would do is try to find the change in temperature first, right? Because you want to find the final temperature. So I would rearrange this equation to get delta T is equal to Q divided by M times C, all right? Now, according to the question, Q would be minus 25.0 joule because of the wording here. It says gives off, right? So that means that the ring is losing heat, which means that the value of Q would be negative as far as the ring is concerned. Divided by the mass. What's the mass? The mass is 5.00 grams, and the specific heat is 0.235 joules per gram degrees Celsius. All right, so the gram units will cancel out, the joule units will cancel out. So your final units at this stage would be degrees Celsius. So let's do the calculation. Minus 25 divided by 5 times 0.235. And according to my calculation, this works out to be equal to, minus 21, how many sig figs? 3 sig figs. So minus 21.3. Minus 21.3 degrees Celsius. All right. Now remember, that's delta T. What the question is asking for is a final temperature, right? So remember now, delta T is equal to the final temperature, T2, minus the initial temperature, T1, right? Now, this is what we're trying to find, right? So if you want to find the final temperature, delta T, that's going to be equal to, T2 will be equal to delta T plus T1, all right? So basically, we put minus 21.3 where delta T is, and the initial temperature is 37.0 degrees Celsius, all right? And let's see what that gives. 37 minus 1.3. According to my calculation, that works out to be 15.7 degrees Celsius, and that would be the answer. That's how you do that, all right? Okay, so it's very important. I can tell you based on past experience, when it comes to these kind of questions, the most common error I would say is the wrong interpretation of the question. Like for example, students not recognizing that giving off heat corresponds to Q being negative, right? So you have to be very careful when you're applying these equations based on the information provided in the question, all right? Okay, any question about this one? Any questions? Any questions? Any questions? Any questions out there in Zoom? Okay, there are no questions, then let's move on. So next topic is, another example. All right. So in this particular case, 1 minute here. I think I have enough space here to do it. Okay, so the question says, a 15.5 gram sample of a metal alloy is heated to 98.9 degrees Celsius and then dropped into 25.0 grams of water in a calorimeter. The temperature of the water rises from 22.5 to 25.7 degrees Celsius. So the question is asking for you to calculate the specific heat of the alloy. So let's see what's happening here. We start off with a metal at a high temperature, 98.9 degrees Celsius, right? And we have water at a lower temperature, which is 22.5 degrees Celsius, right? So what's going to happen when the metal is added to the water is a flow of heat from the metal, which is hotter, to the water, which is cooler, right? And therefore, that flow of heat will continue until both the metal and the water will be at the same temperature, right? So in other words, whatever the final temperature of the water is, the final temperature of the metal is going to be the same. So this value right here, this final temperature, sorry. All right. This final temperature here is not only the final temperature of the water, it's also the final temperature of the metal, right? Okay, so how do we solve this problem? The first thing I'm going to write down here in an effort to solve this problem is this equation right here. The heat change of the metal will be equal to minus the heat change of the water, right? Make sense? The amount of heat that is lost by the metal will be equal to the amount of heat that is gained by the water, right? And that's the reason why we have this negative sign here, because the metal is losing water, so Q is going to be negative for the metal, and the water is gaining heat, so Q is going to be positive. So that's the relationship between those two terms. Now, let me remind you of the equation that we're going to use up top here. And that equation is Q is equal to M times C times delta T, right? What I'm going to do is write down this expression for each of these terms, right? Now, on the right side, on the left side, you have QM, right? That would be equal to, based on this equation right here, the mass of the metal times the specific heat of the metal times the change in temperature of the metal, right? That's on the left side, the QM. And then on the right side, I'm going to have minus mass of the water times the specific heat of the water times change in temperature of the water, all right? So that's the expression we get directly from applying this equation to each of these two terms here and here. Now, the question is asking for the specific heat of the metal, which is this right here, right? So how do we get this by itself on one side of the equation? Well, from your algebra classes, you should remember that to isolate something like this, you would divide both sides by the other terms that it multiplies by. So I would divide both sides by the mass of the metal times the change in temperature of the metal, and you have to do the same thing on this side here, right? So this will cancel with that, this will cancel with that. So basically you'll be left with the specific heat of the metal is equal to all of this right here. And then what we have to do now to find the actual value of the specific heat of the metal is to plug the numbers in, right? Starting off with the mass of the water. So according to the question, the mass of the water is 25.0 grams times the specific heat of the water, which is, again, going to be given to you, 4.184 joules per gram degrees Celsius, multiplied by the change in temperature of the water. Now, what's the change in temperature of the water? It's going to be the final temperature, which is T2 for the water minus T1, right? Now, in this case, that will be 25.7 degrees Celsius minus 22.5 degrees Celsius, all right? So that would be the change in temperature here, right? Then we divide by the mass of the metal. What's the mass of the metal according to the question? 15.5 grams, right? Multiplied by the change in temperature of the metal. Now we have to be careful here. Remember, the initial temperature of the metal is 98.9 degrees. The final temperature of the metal will be the same as the final temperature of the water, which is 25.7 degrees Celsius, right? So basically that would be 25.7 degrees Celsius, that's the final temperature, minus 98.9 degrees Celsius, which is the initial temperature of the metal. And basically what we have to do here from here is to do the calculations. Of course, it's best to work out what's within the parentheses first. So 25.7 minus 22.5, according to my calculation, that works out to be 3.2 degrees Celsius. And then as far as the other part down below, 25.7 minus 98.9. And according to my calculation, this works out to be minus 73.2 degrees Celsius. All right. And then we do the rest. So minus 25.0 times 4.184 times 3.2 divided by 15.5 times 73.2 minus, and according to my calculation, and please correct me if I'm wrong, but I got, okay, how many sig figs I need? Okay, so because of this, I have to round out to 2 sig figs. I got 0.30, right? And the unit for this will be joules per gram degrees Celsius, because the gram units will cancel out here and here. Degrees Celsius will cancel out here and here, right? So basically, this collection of units will remain intact in the final answer, all right? And that's it. That's how you do this problem, all right? Okay, any questions about this one? Any questions? Any questions? Questions? Okay, moving along. Whoops. Clear this first. Okay, let's talk about measuring enthalpy changes in chemical reactions, all right? Oh, by the way, before we do this, before we move on, I gave you guys a copy of the assignment for this chapter, right? I did? Okay, good. So let's take a bit of a detour, see what problems we can do from the assignment number 6. Assignment number 6. Okay, so if I remember correctly, we did questions 1 and 2, right?
Yeah.
Okay, so let's look at question number 3. Question number 3 says a 1.0 gram sample of propane was burnt in a calorimeter. The temperature rose from 28.5 degrees Celsius to 32.0 degrees Celsius, and the heat of combustion is 10.5 kilojoules per gram. Calculate the heat capacity of the calorimeter. Now remember, the heat capacity formula I showed you earlier is uppercase C is equal to Q over delta T, right? So in order to calculate C, we need 2 things. We need delta T and we need Q. Now delta T is the easier part so far because delta T is a change in temperature, right? Delta T is the final temperature minus the initial temperature, which is 32.0 degrees Celsius minus 28.5 degrees Celsius, right? So what does that give? 32.0 minus 28.5. So 3.5 degrees Celsius would be delta T. Now, the question now becomes, how do we get Q? Now, Q in this case is based on information provided here and here, because the question says you're starting off with a 1 gram sample of propane, and the combustion, the heat of combustion is 10.5 kilojoules per gram, right? So basically, to get the amount of heat, which is Q, that would be 10.5 kilojoules per gram multiplied by 1.0 grams, right? So that would be equal to, rounded off to 2 sig figs, that would be equal to 11 kilojoules, right? So to get C now, that would be equal to Q, which is 11 kilojoules, divided by 3.5 degrees Celsius. And whatever that gives, that would be the answer. 0.5. So according to my calculation, this works out to be 3.1 kilojoules per degrees Celsius. And that's how you do that. All right. Okay, any questions about this one? Any questions? Questions? Okay, let's look at number 4 in this segment. Let me clear this verse. Let's go down. Okay, so in the case of number 4, it says when 72 grams of a metal at 97 degrees Celsius is added to 100 grams of water at 25.0 degrees Celsius, the final temperature is 45.5 degrees Celsius. What is the heat capacity per grams of metal? And it says that the specific heat of water is 4.184 joules per gram Celsius, right? Okay, so this question is kind of worded in a kind of tricky way because the question is asking what is the heat capacity per grams of the metal, right? The heat capacity per grams of the metal is the specific heat, right? So basically the equation that you're going to use is Q is equal to M times C times delta T, right? Okay, now, let me just add a decimal point here. That's a typo. So make sure you include a decimal point when you're working this problem. Okay, this question is very similar to one of the examples that we just looked at a while ago, right? So I want you to look at this question and tell me how would you go about approaching this? You're starting off with metal, which is at 97 degrees, and you're dropping it in the water, which is at 25 degrees, and then it says the final temperature is 45.5 degrees Celsius. So the temperature of the metal is falling, the temperature of the water is rising until they're both equal, right? Okay, so let me hear what you have to say about solving this problem. What would be your first step? And feel free to look at the example that we looked at earlier. Excuse me. And you guys out there in Zoom, please feel free to chip in as well with your suggestions.
We're gonna have to make the 2 equations again.
I'm sorry?
We're gonna have to like combine the 2 equations again.
Okay, so tell me what to write now.
So the mass of the metal. And
Mhm.
then, pretty much the same thing.
Right, Cm
Cm and
times delta T.
Yeah.
M is equal to the mass of the water times the specific heat of the water times delta T of the water. So if you remember, after dividing both sides by M of the metal and T of delta T of the metal, we end up with Cm is equal to the mass of the water times the specific heat of the water times the change in temperature of the water, all divided by the mass of the metal times times delta T of the metal, right? Now the trick is, well, not the trick, but you have to be careful about, what numbers you're going to put for each of these terms, right? So what is the mass of the water based on the question? Based on the information in question, what's the mass of the water?
4.184.
Nope, the mass. 100 grams, exactly. And then what you said, 4.184, that's the specific heat. Joules per gram degrees Celsius. Okay, what's the change in temperature of the water? Be careful about this part. This is where students tend to make most of their errors when it comes to these problems. What's the change in temperature of the water? What was the initial temperature of the water?
25.
25. What's the final temperature? 45.5, right? So the change in temperature of the water will be what?
20.5.
Let's put the numbers first.
45.5.
45.5 degrees Celsius minus 25.0 degrees Celsius, all right? And then we divide by what? The mass of the metal. What's the mass of the metal?
72.
72 grams. And what's the change in temperature of the metal? What was the initial temperature of the metal? Oh, by the way, I forgot to put the negative sign here. We should be here. We should be here, all right? So please include that, right? Okay, so what's the final temperature of the metal?
Final or the original?
Final. Because remember, it's final minus initial when it comes to the change of anything, including temperature, right? So,
Should be 45 minus 9
For-
left.
right, so it's 45.5 degrees Celsius. That's the final minus the initial, which is 97.0 degrees Celsius. And that's it. So let's work out what's within the parentheses first. So that's 45.5 minus 25.0. And this part here works out to give 20.5 degrees Celsius. And then for the bottom part, 45.5 minus 97.0. And according to my calculation, this is minus 51.5 degrees Celsius, right? And then we do the rest of the calculation. So 100 negative times 4.184 times 20.5 divided by 72 times 51.5 negative. And according to my calculation, how many sig figs now? 2 sig figs. So according to my calculation, this works out to be 2.3. And the units again will be joules per gram degrees Celsius. And that's how you do that. All right. Okay, any questions about this one? Okay, so let me clear this here. Let me see if there are any more questions we can do from this assignment here. Oh, here's one that's interesting. All right, we can do here 5, 6. Okay, we can do 5 and 6. All right, so let's start off with 5. What is the resulting temperature when 35.0 grams of water at 75 degrees is mixed with 15 grams of water at 10 degrees Celsius? All right, and again, it gives you the heat capacity. Well, actually, that's the specific heat capacity of water. All right, so let me hear some ideas as to how you tackle this. They gave you, in this question, they gave you, excuse me, they gave you 35 grams of water at 75 degrees Celsius and 15 grams of water at 10 degrees Celsius, all right? And then you're going to mix them, right? So how would you start off solving this problem? How about you guys out there in Zoom? Any ideas? Okay, let me give you a little hint, right? So think about this. What will happen if you add hot water to cool water?
Or warm, yeah.
What's that?
Not or warm, like warm water instead of hot water.
Well, the warm water or the, well, yes, you're right. Because what's going to happen is that the temperature of the amount of water that is added that is hot would fall, and that of the cooler water will rise. So the temperature will be somewhere in between. So it's kind of similar to the problems that we just looked at when we add a hot metal to cooler water, right? So how would you represent this mathematically? Well, you could say Q of the hot water will be equal to minus Q of the cooler water. All right? So, what next? What would you do next after writing that relationship down?
Set it up kind of like before.
Exactly. So tell me what to write down. Let's deal with the hot water first.
So we have 35 grams of,
Well, before we put the numbers in, I need the equation,
oh,
the symbols for the
you want
difference,
to just do like M of H,
right? Mass of the hot water times
CH,
CH times
TH.
delta TH, right? And then on the other side, you're gonna have minus
MC,
MC times
CC,
CC times
delta T.
delta TC, right? Okay, very good. Now here is one difference between this problem and the other problems that we looked at. It's the same substance being added together, which means that the specific heat will be the same for both the hot and cooler water. So that simplifies things. This will cancel out with that as a result because they're both the same. You see what I'm saying? Let's continue now. Let's see here. So basically this reduces to MH times delta TH is equal to minus MC times delta TC. All right. Okay, so let's put some numbers in. The mass of the hot water is 35.0 grams, right? Times the change in temperature of the hot water, delta TH, which is what? What's the change in temperature of the hot water?
Would be the 75 minus 10.
Nope. Because remember, 10 is the temperature of the cooler water before you mix them together, right? And remember the question is asking for the resulting temperature, right? That resulting temperature will be the final temperature, which is T2, which is, T2, right? So to calculate delta TH, we can't really calculate it yet. All we can say is delta TH will be T2 minus the initial temperature of the hot water, which is 75 degrees Celsius, right? And then on the other side, you're going to have minus the mass of the cooler water, which is 15.0 grams, multiplied by delta TC. Now, what would that be? What would be the change in temperature? It's kind of similar to this here. What would be the,
Plus 10.
I'm sorry?
T2 plus 10.
No, it would be T2 minus 10 degrees Celsius. All right. So basically, all we have to do from here is some algebra to solve for T2. All right. I'm going to need some more space. So let me erase the stop part here. All right. So what I would do, there are several approaches you could take. What I would do, let me see. How am I going to do? Okay. What I would do is divide both sides by minus 15.0 grams. Right? So that this will cancel out with that. And let's see what that gives. So 35 divided by 15 gives 2.33. So I'm just going to continue up here. 2.33 times T2 minus 75 degrees Celsius equals to T2 minus 10 degrees Celsius. Oh, and also add a decimal point here. That's another typo for the 10 degrees Celsius. All right. Okay. And what I'm going to do now is, what's the term they use in math? Distribute. I'm going to multiply 2.33 by everything within the parentheses. I'm going to end up with 2.33. I'm sorry, yes, ma'am.
Wouldn't it be the 2.33 being negative since you're dividing by negative?
Yes, thank you. You're right. Very important. Right. So minus 2.33 times T2, and then because of this negative, this becomes positive. So 2.33 times 75. So that gives, according to my calculation, 170. So it'll be plus 170 degrees Celsius equals to T2 minus 10 degrees Celsius. And then now, to get like terms on both sides, what I will do is I would add 10 degrees Celsius to both sides. And I would add 2.33 T2 to both sides. So that this will cancel out with that, this will cancel out with that when you continue over here. So you're gonna end up with 170 plus 10 gives you 180 degrees Celsius is equal to T2 plus 2.33 T2 will give you 3.33 T2, which means that T2 will be equal to 180 degrees over 3.33, and according to my calculation, that would be equal to 54 degrees Celsius. And that would be how that is done. And that makes sense because 54 lies in between 75 and 10, right? So that's basically how you would do that. Okay, any questions about this one? Any questions? Any questions? Okay, moving on. Let me clear this here. And let's move on to number 6. Okay, so number 6 says a sample of cobalt A with a mass of 5.00 grams is initially at 25 degrees Celsius. When this sample gains 6.70 joules of heat, the temperature rises to 27.9 degrees Celsius. Another sample of cobalt B with a mass of 7.00 grams is initially at 25 degrees Celsius. If sample B gains 5 joules of heat, what is the final temperature of sample B? So again, you'll be using the same equation. Q is equal to M times C times delta T, all right? Now, you have two samples of the same element. So because they're the same element, the same substance, that means that the specific heat will be the same. That's going to make life a bit easier for us. So let's see how we can work this. Let's deal with the sample A first. They gave you the mass, they gave you the initial temperature, they gave you the final temperature, and they gave you the heat, right? So basically you have everything you need in order to calculate C. So let me just write down here for sample A. C is going to be equal to Q over M times delta T. So all I did was rearrange this equation to get this, and then I'm going to put the numbers in. So Q is equal to 6.70 joules over the mass, which is 5.00 grams, times delta T, which is the final temperature, which is 27.9 degrees Celsius minus 25.0 degrees Celsius. So again, I'm going to work out what's within the parentheses, which is 27.9 minus 25. So this part here, I calculate that to be equal to 2.9 degrees Celsius, and then I'm going to do the rest of the calculation. So 6.70 divided by 5 times 2.9. And according to my calculations, I have to roll this up to 368. So this will be equal to 0.462 joules per gram degrees Celsius, right? So that's the specific heat of cobalt based on the numbers given for sample A. Now, what we need to find now for sample B, we need to find the final temperature. In order for us to find the final temperature, we need to find out the change in temperature, right? Because they gave us the initial temperature, so we can find out the final temperature. So for sample B, I'm going to rearrange this equation again, but this time I'm going to find delta T. Delta T will be equal to Q over M times C. So for sample B, Q is 5.00 joules, M is 7.00 grams, and C is what we just calculated here, which is 0.462 joules per gram degrees Celsius. So let's see what this gives. 5 divided by 7 times 0.462. Okay, so according to my calculation, okay, according to my calculation, this is equal to 1.55. Now, one thing I forgot to mention here, which doesn't affect this answer right here, but I forgot to mention about how the question is worded. The question says that the sample gains 500 joules of heat. So that means that this is positive, right? Very important. Because the question could have been worded differently, right? The question could have said, it loses 5 joules of heat, in which case you'd have to put negative here, but it's positive, so that's fine, right? So this is delta T. Now remember, the question is asking for the final temperature. Delta T is equal to T2 minus T1. What the question is asking for is T2. So therefore T2 will be equal to delta T plus T1. Delta T, we just calculated here, which is 1.55 degrees Celsius, plus T1, which is, in the case of sample B, is 25.0 degrees Celsius. So this works out to be equal to, rounded off to 1 decimal place, that would be 26.6 degrees Celsius. And that's basically how that is done. All right. Okay, any questions about this one? Any questions? 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 Okay, I think that's as far as we can go as far as the assignment is concerned. Because let me see here. Let's see. Okay, I don't think we can do this yet, so I need to cover some other things. Okay, so let me go back to the PowerPoint and see here. All right, so whenever we're talking about doing experiments to determine the amount of heat change, using calorimeter, this is the basic relationship between the heat change of the reaction and the heat change of the calorimeter. Q reaction is equal to minus Q of the calorimeter. And therefore, Q of the calorimeter, based on the contents within the calorimeter, would be mass times the specific heat times the change in temperature, right? So basically, we have to use the specific heat of the contents in the calorimeter in order to use this equation so we can determine the Q of the calorimeter, and therefore we can assume that the Q of the reaction would be the negative of that value, all right? And then based on the Q of the reaction, we can determine the enthalpy change, all right? Okay, now this example here, do we have enough time to?
Yes.
Okay, let's do this first equation here, first example here, and then we'll call it a day. So let me copy, I'm gonna need space for this. I'll show this. Okay, so the question says you have a 50 ml sample of 0.250 M hydrochloric acid at 19.5 degrees Celsius is added to 50 mLs of 0.250 M sodium hydroxide at 19.5 degrees Celsius. So you're adding hydrochloric acid to sodium hydroxide. The molarities are the same, the volumes are the same, and the initial temperature are the same for both of them, right? So that makes things a bit easier for us to work with. Then it says, after mixing, the solution temperature rises to 21.21 degrees Celsius. Calculate the heat of this reaction. Okay, so how do we go about this? The first thing we need to do is to find out. There's some assumptions, and they should have stated this in the question, right? Let me write down the assumption. For one, well, this is not an assumption, this is an actual fact. The density, well, actually, it's an assumption. The density of each solution will be 1.00 grams per mil. We have to assume that, right? Because these solutions are basically aqueous solutions, and because the concentrations are relatively low, the density is about the same, all right? That's one assumption that you'd have to make. And then, there's also another assumption which I think you have to make. I guess I'll get to it, in the process of solving this problem. So basically what we need to do is find the mass of each solution. So the mass of each solution will be 50.0 mils multiplied by the density of 1.00 grams per mil. So that's going to be equal to 50.0 grams, right? And the reason we can do that is because the volumes are the same for each solution, right? So the mass will be the same because the volumes are the same and the densities are the same, all right? So we know that we're working with 50.0 grams of solution each, and the total mass upon mixing would be equal to 50 plus 50, which would be equal to 100.0 grams, all right? Okay, now to find the Q of the reaction, that will be equal to mass times the specific heat times delta T. Oh, I remember now. The other assumption we have to make is that the specific heat of the solution is 4.184 joules per gram degree Celsius, even though it's not pure water. But again, because the solutions are dilute, then you can assume the specific heat of the solutions to be the same as the specific heat of water. All right, so all we have to do is put the numbers in. Now the mass of the solution combined would be oh, wait a minute, hold on. I have to mix in the solution. Okay, so let me put the numbers in. 100.0 grams times C, which is 4.184 joules per gram degree Celsius, multiplied by the change in temperature. What's the change in temperature? It's the final temperature minus the initial temperature. So that would be 21.21 degrees Celsius minus 19.5 degrees Celsius. So again, we work out what's within the parentheses, 21.21 minus 19.5, 0, 1.95, 19.50. So this part here works out to be equal to 1.71 degrees Celsius, and then we multiply that by 4.184 times 100. So according to my calculation, the Q of the reaction is going to be equal to 7.1, I'm sorry, seeing doubles. This should be 715 joules, because the gram units will cancel out, degrees Celsius will cancel out, so you'll be left with joules. So this would be the final answer, all right? And that's it for that question. Any questions about this? Any questions? Now, in the time that we have left, I'm just going to quickly refer to the other question. The question says, express the results of the previous question for molar amounts of the reactants. That is, determine what delta H is equal to. Now, in order for you to do that, going back to this, what you'd have to do is determine the moles of each of the reactants. And we can easily do that because they gave us the volume and the molarity of each solution, which is the same for both of them. So the number of moles of sodium hydroxide will be equal to the number of moles of HCl, which will be equal to 50.0 mils. We have to convert that to liters, 1 liter over 1,000 mils. And then we multiply that by the respective molarities, which is the same in both cases, 0.250 m or moles per liter. And let's see what that gives. So 50 divided by 1,000 times 0.250 According to my calculation, this works out to be 0.0125 moles. And then, to get what the question is asking for, basically, on a per molar basis, we take the Q here, which is 715 joules, and divide it by the 0.0125. Moles, right? So Q reaction per mole is what the question is asking for at this stage. So we take the 715 divided by the 0.0125, and according to my calculation, this works out to be equal to 57200 joules per mole. Did they specify what units? Let's see. Okay, they didn't specify the units, so you can leave it as joules per mole. All right. So this will be the final answer. All right. Okay. Any questions about this one? Any questions? Any questions? Any questions on there in Zoom? Okay, so before you leave, just to remind you of a couple of things. I won't be around tomorrow, so you won't be able to reach me if you have any questions during my normal scheduled office hours. I will be out of town. So just to let you know about that. And also just to remind you that your test number 2 will be on Tuesday of next week. All right. I'm still in the middle. In fact, I should be finished with grading your assignment number 5. So I'm hoping to have that sent back to you. If not later on this evening, definitely early tomorrow morning, right? In the meantime, I think you have noticed that I've posted the answer keys for assignment number 5, right? So in the meantime, you can review that because your test, of course, will be based on chapters 3, 4, and 5, right? 3, 4, and 5. You should already get your graded work for assignments 3 and 4. This is the only one that's left as far as this test is concerned. So I'm going to try to get that back to you later on today, but if not today, definitely by tomorrow morning. All right. So that's basically all I have to say by way of announcements, unless there are any questions or issues. If not, that's it for today, folks. I'll see you guys next Tuesday. You too. Okay. So you guys out there in Zoom, I'm gonna sign off now.